In this video, we're going to look at finite differences. Now, when we say finite differences, we mean things like the first differences, second differences, third differences, and so on. So those are finite differences. So what do I mean by first differences? Well, in order to find first differences, and what we'll do is we'll look at this table, we'll go ahead and find the first differences. We first want to make sure that the table is organized in order, first of all, and that the x values are going up by the same amount. You can see here that we're going up by 1 every time, so the x values are going up by the same amount. Just a reminder, maybe we'll jot this down off on the side here. If I wanted to look at this information in the table, I could find the rate of growth here. The rate would be the change in y divided by the change in x, sometimes called the rise over the run. Change in y divided by the change in x. So that would be the sort of difference here. That's kind of what we're looking at. And the nice thing here is that if we're going up by ones all the time here, then the rate of growth, or the growth that would happen here, sometimes called the rate of change, would just be equal to whatever the change in the y values are. So these f of x values, these function values, would be our y values. Let's go ahead and find out what the first differences are here. So I will make a column for first differences. We'll just call it first differences, diff for short. And in order to find those first differences, what we're really doing is we're saying, well, how much do we need to sort of increase or decrease to go to here? So what we can do is we can take that second option and subtract the first one. 0 minus 5 will give us negative 5. That means that we're subtracting 5. So to go from 5 to 0, we're subtracting 5. And we just repeat that sort of pattern all the way down. And we're going to take negative 3 and subtract 0. And we'll get negative 3. Next up will be negative 4. Subtract negative 3. Sorry, let me fix that up for you. That's hard to read. Subtract negative 3. I'll just put it like this. I was going to put a bracket in, but maybe that's confusing. Sorry, let's try that again. Yeah, negative 4, subtract negative 3. So that's kind of like adding 3 to negative 4. So that's going to take us to negative 1. And then we'll do negative 3, subtract negative 4. So that's like negative 3 plus 4. That'll give us a positive 1. 0, subtract negative 3. That's the same as 0 plus 3, which is 3. And finally, we have 5 minus 0, which is equal to 5. So we can see here that these are our first differences. They are not all the same. And as you may recall from earlier courses, that's an indication that this function and the graph for this function will be nonlinear. So let's take things one step further. I've just put that information in a table for you. So here's our function. Same values. Here are our x values. Here are our function values. Here are our first differences. And now what we could do is we can look at what's called the second differences. And the second differences are just the differences of the first differences. So we repeat the process that we followed before. I want to figure out, what do I have to add or subtract to go from negative 5 to negative 3. So I'll start with that negative 3. I'll subtract negative 5. Negative 3 minus negative 5 is the same as negative 3 plus 5, which will take us to 2. And then we just repeat that whole process all the way down. So negative 1 minus negative 3. That's like negative 1 plus 3, which will take us to 2. And then here we'll do 1 minus negative 1. Also 2. You can probably see a bit of a pattern here. 3 minus 1 is 2. And finally 5 minus 3 is also equal to 2. So these are the second differences. And again, the x values are organized sort of from lowest to highest, but the important thing here is that they're actually going up by the same amount every time. Sorry, I just noticed this should be a negative here. So they're going up by the same amount every time. And we saw that the first differences weren't equal, but we do see that the second differences are in fact equal. And what this tells us, if we were to graph this function, is that we would get a parabola. So this function would create a parabola or a quadratic function. Well, let's backtrack a little bit. Maybe we'll just do a rough sketch of this. It won't be very precise, but we can see here that when x is -2, y is 5. When x is -1, y is 0. Whoops, that's not -1. When x is -1, y is 0. When x is 0, y is -3. When x is 1, y is -4. And when x is 2, y is -3. So we see that we just found the vertex. And when x is 3, y is 0. And finally, when x is 4, y is 5. So we get this kind of symmetrical looking parabola. So whenever you have first differences that are, if the first differences are, let me backtrack. If the first differences are the same, we know that the function is linear. If the second differences are the same, then the function is quadratic. So here's an example. This is an example here where I mentioned earlier about how the x values need to be in order. So it looks like they are here in order. We're going down by 2's until we get down in here, and all of a sudden, and the table of values doesn't have to be in order, but if we want to find these first differences and make sure that they're the same, we probably want to make sure that these are in order. So you can see here, if we reorganize this table so that we're going in order from smallest to greatest, we can see that there's a constant change here. So the x values are constantly going up by 2, plus 2 all the way down here. And when we do that, the first differences are 4. If we were to graph that, we'd get a nice straight line here, indicating that this is a linear function. So as I said earlier, if the first differences are the same, the function values are increasing by the same amount, and that gives us a linear function. If the second differences are the same, then the function is quadratic. Now what happens with an exponential function? Let's go through and just quickly look at the differences here. We can find the first and the second differences. Oh, that's not the right spot. Let me just see if I can just clear my screen a little bit. There we go. So if we're looking at the first differences, we can see that from here to here, we are going up by 6. And from here to here, we're going up by 18. So right away, we can see that the first differences are not the same. We probably didn't even need to go this far, but here we're adding 54. Here we're adding 162. And from here to here, we are adding 466. So those were the first differences. They were not equal. Let's look at the second differences. So again, looking from here to here, 18 to 6. I've kind of drawn these arrows the wrong way, haven't I? I'm sorry. This was an increase of 12 from 18 to 54. That would give us an increase of 36. 162 minus 54 gives us 108. And finally, 466 minus 162 gives us 324. So again, the second differences are not the same. That tells us that this function is not a quadratic function. We already know it's not a linear function. This function is actually taken from a function that we would have looked at earlier. Number of days and the number of people who got sick, for example. And the graph looks like this. And when you look at the graph, you can see that it's exponential. And the way that we tell that the function is exponential from the table is not with a first difference or a second difference, but with what we call a common ratio. So the common ratio is kind of like a first difference in that we're comparing successive y values, but instead of looking for an increase or a decrease, what we're doing is we're taking the second y value and we're dividing it by the first one. So here we got 9 divided by 3, that was 3. We also see that from here to here, we're doing 27 divided by 9, which is equal to 3. 81 divided by 27, which is equal to 3. 243 divided by 81, which is 3. And you can kind of see the pattern here. I'm out of space there for that last one. So for an exponential function, it's not that the differences are the same, that the finite differences are the same, but for the exponential, function, it's that there's a common ratio. So we take successive sort of y values and divide them by the previous, just like we did with the differences, except instead of subtracting, we're dividing. And that's how you can tell if a function is exponential from its table.